You may be asking yourself, why have we been bothering with all of these series tests? What's the point? I mean, you can add up an infinite number of fractions as an interesting problem, but is there actually a use for all of this? Now, we did see that geometric series do have some applications for describing real-world processes like bouncing balls or epidemics or economic transactions, but other than that, most of these series tests may feel very, very abstract at this point. So what is the point? Well, the purpose of manipulating infinite series is not really just to add up a bunch of fractions. Those are interesting puzzles. That's really just a stepping stone to what we're actually interested in. And what we ultimately want to be able to do is not add up just fractions, but add up functions. In fact, we're going to focus primarily in this class on adding up polynomials, but another useful thing you might want to do is add up sines and cosines. And in physics, that's a vital technique for describing anything that oscillates or vibrates. Now, so there's lots of math problems where we might want to do this because the problems themselves are quite difficult. It's not at all uncommon to have a scientist come up with the equations to describe some physical system, only to realize that what he's got is something that's too hard to solve or that involves a function that no one has ever really studied before. And so when you're faced with a problem like that, what do? Well, we're going to look at a theorem in these last two chapters that shows us that we can write just about any function as an infinite sum of polynomials. And this is important because we know how to take derivatives of polynomials, and we know how to take integrals of polynomials. And so this is going to allow us to take a problem that would otherwise be impossible and make it much more manageable, as long as we're willing to live with infinite series. And it's also important because it gives us a way of using computers to calculate the outputs of transcendental functions like sine of x or e to the x. Now, you may not realize this, but computers are actually not very smart. They only really know how to do a few basic tasks. They know how to add, they know how to subtract, they know how to multiply, and they know how to divide. But anytime you want to use your calculator or your computer to do something like compute the sine of x or e to the x or even a square root, it turns out that actually the way to do that is to reduce those more complicated calculations into those basic operations of adding, subtracting, multiplying, and dividing. But how do we do that? Well, the types of functions that only involve adding, subtracting, multiplying, dividing are polynomials, right? For a polynomial, you need to know how to multiply by a constant. You need to know how to take a number represented by x and multiply it by itself multiple times, and you need to be able to add up a bunch of different terms in the polynomial. That's it. So if we can write a function like sine of x as a sum of polynomials, then we could use a computer to help calculate sines and solve other math problems involving these sorts of functions. But there is one additional problem, and that is that computers can only work with finite sums, right? You can't have a computer add up an infinite number of things. That would take forever. So this is only going to work if we can find a way to approximate an infinite sum with a finite sum. Well, the good news is we've already looked a little bit at how to do that. We've looked at alternating series and seen how we can actually truncate the sum at a certain point and estimate how far off an estimate would be from the true value. We also looked at using the integral test to try to come up with a range of estimates for particular sums. And so that's a useful technique for understanding how do we make approximations with infinite series, how do we truncate the series and use a finite sum instead, and know that our estimates are actually going to be reliable. And the only way that we can actually do this is if we actually understand some of these series tests to be able to show that, one, the series converges, and two, talk about how quickly it actually converges. Now, to further set the stage for one particular problem where this idea is useful, let's look at a classic physics problem, which is that of a pendulum. Now, we're not going to get into all of the details of this problem, but I will kind of summarize the big picture, and that is that if you want to describe a pendulum, which a pendulum you can think of as a mass suspended from some sort of rod that's moved, rotated around a pivot point, and let's say that there's some angle theta that the arm of the pendulum makes from vertical. What you might want to do, if you're a physicist, is actually describe the motion of the pendulum, and that would require using Newton's laws to describe how fast the angle is changing over time. And if you do that, if you apply Newton's laws, again, we'll not derive this carefully, but essentially what you end up with is something that looks like the second derivative of theta with respect to time is equal to negative the sine of theta, potentially with some constant out front. And this is basically, it comes from mass times acceleration. And we've divided out by the mass in this case. And then the other term comes from this sum of the forces. And in this case, the forces are due to gravity, and gravity acts downward. And so if you want to find the component of gravity that's actually causing rotation, it's related to the sine of theta. Okay, so there's an equation that physicists might want to solve. There's just one problem. This is what's called a differential equation, which means we have some unknown function, theta of t, right? Theta changes over time, and we don't know how to find it. Because this particular differential equation, which tells us the second derivative is equal to negative the sine, does not have a nice solution in terms of functions that anyone's ever heard of. Well, that's a problem. We can't write down a nice exact solution. You can come up with some sort of estimate for the solution with a computer, but if we want to actually find a formula for the answer, it's going to be quite difficult. So how do physicists approach this problem? Well, they use this what's known as a Taylor series, an infinite series, to approximate the sine. And let me show you what that looks like. So I'll bring up Desmos here. All right, so here I've got in black the sine of x graphed. And what I'm plotting right now is an infinite sum that converges to the sine of x. And in this case, you'll notice that inside the sum, I have a term x raised to some power. And this is going to be an example of a power series, which we'll be talking about in the next few videos. All right, so we have a function in our sum rather than just a fraction. And currently, I'm using a partial sum with just one term, which means essentially we're just adding up one function. And in this case, the function is just x. And you can see that when I add the graph of x, it fits perfectly over the red curve. Okay, so at the moment, this is really just a tangent line. And you'll see that if we were to zoom in really close near the origin, the tangent line does behave a lot like sine of x near 0. But once we get far away from 0, it no longer gives us a really good approximation. So the tangent line is a good approximation that is works for over a narrow range of angles, or in this case, x values. But if we want an approximation that's a little more accurate that works over a wider range, that's not going to help us. So what can we do? Well, we can add the next term in this series. So let's go out to d equals 2. And you'll notice at that point, the next power of x is going to be an x cubed. And if you plug in n equals 2 here, you'll get negative x cubed over 6. And you'll see that now we have a new polynomial that seems like it hugs the sine function over a wider range of x values. And if we add the next term, x to the 5th over, how about 120? Let's see, is that right? Yeah. Okay, it even hugs it for longer. And as we add more and more terms, look at that. This polynomial, which is just adding up different powers of x, seems to hug the sine function very, very, very closely over a wide range of values. Now, remember that the sine function is periodic. So once you know what happens between negative pi and pi, once you can get good estimates there, it's easy to get good estimates everywhere. And so at this point, you can zoom in really close. Let me zoom in around pi. And you'll see that, I mean, our approximation is pretty much indistinguishable from the true function. This is with 13 terms, so it's got a little more than that. But it's almost indistinguishable from the sine function, which means we can get really, really reliable estimates of the sine function between negative pi and pi using a polynomial. All right, and so how does that help us solve our original problem? Well, if we want to solve this equation, we could say, well, that's too hard. Let's solve an easier equation. Sine of theta is approximately, well, if we use the linear approximation, we'll just get theta. So we have theta double prime, the second derivative of theta with respect to time is equal to negative theta now, or at least approximately equal to. And so now we're just looking for a function that its second derivative is the negative of the original function. And there are probably two functions that come to mind that have that property. The sine of t. If you take two derivatives, one derivative would give you a cosine, another derivative would give you a negative sine, so it changes the sign. And then a cosine would as well. Take a derivative of cosine, you get negative sine. Take a derivative of negative sine, you get to negative cosine. And in fact, if you take any combination of those two, so you multiply them by constants and add them together, then you would get a solution that satisfies this equation. Once you know exactly what the initial angle is, you can find exactly what those constants A and B should be. And that tells us that ultimately what's going to happen with a pendulum, well, when you let the mass go, it's going to just go up and down, something like this. Some sort of oscillation described by just sines and cosines. Now, that's just an approximation, right? We changed the equation slightly. We threw the sine of theta away and replaced it with a theta. And if we're not happy with that approximation, maybe it's not accurate enough, well, we say, let's just take the next term in our series, which would be theta cubed over 6. And that equation is going to be a lot harder to solve. I won't actually go through the solution there. It's a lot trickier, but you can actually still solve it exactly. And you can get a solution that looks very similar to sines and cosines, but it's going to be slightly different. And if you look very closely, you will notice some distinctions there. Okay? And in fact, we can continue to add more and more terms to make this equation as accurate as we want so that it approximates the original problem. But the benefit of this approach is that we don't have this complicated function sine of theta. We have just polynomials that we have to work with. Okay? So that's ultimately the goal. The goal is to be able to generate infinite sums of polynomials or finite sums as an approximation to replace complicated functions and to turn hard problems that we would not otherwise be able to solve into easy problems.